Alright, another draft physics video presentation. Yeah. Anyway, so I'll do a couple of comments. It might take a while. And then, photons and relativity. And then move on to maybe Sean Carroll on matter. Okay, so that ought to be kind of funny. There was a email I got with somebody, I don't know, logical imperialist, I don't know who, one of these people that hates me but doesn't totally hate me or some kind of crap. Anyway, he posted a link to the physics in some place called Rational Skepticism. And it's just, the fact that it's just such a waste of time to have a conversation with these arrogant putzes, right? Because it's all just jokes. I mean, a daft joke, and then draft joke like draft beer. And, and they're all so full of themselves. They're all quoting great minds of history as their little taglines, and it's just crap. I mean, crap. So anyway, these will be fun people to make fun of in the future. Just look how what a serious skeptic you people are, right? Just defending the religion, and somehow vaping now is it's always we're back to what? The cool people think it's cool just to say pothead or something. I mean, it's like we're going backwards. It's like the 40s, women started like dressing in burqas in America, and in the 20s they were almost wearing nothing. And, some same sort of cultural revolution. So somebody has an icon on a science type channel of a hyena. Yeah, right. You're a serious human. Anyway, but just all crap. They didn't watch a minute of the video, and they just do this crap. And you're just like, what a waste of time. Rational skeptics. Yeah, sure you are. So anyway, I'll leave a link below just because it's just funny that they don't even come close to the subject. Nowhere near it. Just a complete waste of time. Demonstrated once again that these science types don't really give a shit about the truth, having any integrity to their science. They just care about their religion. It's a religion, and they don't want to be bothered defending it. Plain and simple. Anyway. Amazing how embarrassing long it takes to find the right words. Yes, it is tough. Polarization. Months ago I asked if it wouldn't be destroyed by the radial spread, and you denied that. So I don't know what the context of that statement is, so there's no real point in me saying I don't know if that's true or not true, but whatever. I have pointed out that this is a photon, okay? So just think of this space as just being a container, but this is all the photon is little dots in, these are supposed to be equally spaced, and the spacing should be the same as this height. So they should be the same distance this way as they are spaced from each other. So it's not exactly accurate. But the idea is this is how it travels through space. It doesn't have any of this. So as I pointed out, if you draw your traditional wave, you have to understand it has a length. Photons aren't indeterminately long, okay? They don't have an indeterminate number of nodes in the sense that the ones we can see have to have a certain number. The ones the frog sees are a different number. So I could cut this in half, and that's a photon a frog could see, right? But the idea is this is what's traveling through space. Something that has, dimension this way, but has very little dimension this way, all right? And it has pieces of momentum in it. It has a length. Ding, bing, 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 bing. You can have 4 little bings. You can have 9 bings. But that's it. And so it can fly this way and this way and this way. So you can understand how this little thin piece of paper could occupy different places in space in all kinds of ways. And it could take a lot of little pieces of paper to actually fill a piece of space. You could stick a lot of these pieces of paper in there. Alright, so that's the idea of a photon. It's just impacts on a surface. More fundamentally, alright, we'll get to the more fundamental argument. I've tried to explain that eventually, okay, where I will be going with this, you know, as an argument, is that this is what the universe basically is. Okay, there's a thing, and then there's stuff in the universe flying into the thing. Okay, the forces, the force. And the idea is the force always moves the speed of light. And let's say this thing is capable of doing that, just for the sake of argument. It's probably half the speed of light, so it makes it a little more complicated. But anyway, so a thing hits it, and this thing actually changes its position. Okay, so it goes from being there to, say, going to being here. Now you can understand in this new position, when it's moving into this new position, it's moving into these forces that are coming this way. That's going to reflect. So you can understand that it would have reflected this piece here. From here, this piece would be way back here. Because it's moved here, okay, this piece is now here. So this piece of energy, the piece of energy that came in, is going to have, there's going to be a change in the universe in the sense that you've changed the position. And likewise, if it moved over here, okay, then this thing would be way behind, way over here. So in a sense, there would be an empty space here. So you can sort of understand, I stated it. If I moved the speed of light away from the camera, I would be invisible. Okay, nothing. Nothing would be sent to you from me at all. And if I moved towards you, at the speed of light, everything in that space would end up being something you'd see. So I would take all of whatever, this arrow and this arrow and this arrow, they'd all be going this way, and all of a sudden they'd all be lined up going this way. Okay, they'd all acquire a consistency, and that's what's creating photons. Is electrons, when they move, okay, they change their position, they change what happens as terms of a reflection. So when they move away, like into a surface, the surface doesn't reflect anything. That means there was a bunch of arrows going this way, all right, all of them don't hit, none of them hit the surface because it's moving away. So there's nothing going this way. I can't draw nothing going that way, but I mean there's nothing. There's an empty. Then when it stops, okay, then a bunch of stuff starts hitting it, okay, and so then there is stuff. And so that's sort of the idea, that you can sort of understand that what photons are is creating the void in between them. These empty spaces, okay, where you have stuff and then you have no stuff. So depending on how an electron moves, there's that cord again. Stop that, please. I said please. Do you not understand the concept? Anyway, so you can see that, right? Yeah. So that this starts to create the frequency, right? So you can see that if a frequency came in at a certain speed, you could understand how, because of how the electron moves, the frequency could be changed. And so, distance, force that came at this rate could end up coming at this rate, or this rate. And it could be varied based on how the electron moves and how it reflects the universe back to the world. So that's, I would say, the more elemental way to understand the creation of a photon. Now, the other argument to make about how it happens mechanically relates to the fact that we know that all this stuff is on a spectrum. And we know that the radio waves require a really long antenna, right? And that a microwave requires a little tiny antenna. Well, we don't all know this, okay? So that's the problem. And it really has to do with the speed that you can send a signal, right? It has to move the speed of light. So obviously, at the speed of light, if your frequency is 3 centimeters, okay, like microwaves, then all you can get is 3 centimeters worth of antenna that's going to be effective. If I have a longer antenna, it can't send the signal through that antenna and send something relevant here. It's going to be irrelevant because it's going to be out of sequence. The frequency is going to be destroyed by the fact that it takes too long to get here. Okay, getting here to send something before you send it, the pulse, it's going to be out of sequence, so it's going to be useless to you in terms of sending your signal. Your signal has to be capable of getting through the antenna and be sent at the right rate, right? One piece sent from here, and then a little piece sent from here, and a little piece sent from here, a little piece sent from here, sent from here. The extra antenna is not going to do any good. And the same on the receiving end. You have to receive the polarization that was sent, so the same idea is going to exist, is that this extra antenna is not going to do you much good. Because the signal won't be coherent. If you have a longer antenna, it takes too long for the signal to get down here, and so now it's lost its phase relevance, so it's just not effective. So the point is that light has this little tiny antenna. There really is an antenna. You could argue that the atoms, all right, an arrangement of atoms in a crystal. See, the things that do this stuff really well are crystals, metals, and that these crystals can be in different positions. But the idea is this surface. Okay, the stimulus runs through the surface and creates the photon. Okay, the sequence. So you'd say this one came first, second, third, fourth, fifth, right? Going this way. If the electricity was going this way, it'd be the opposite if it was going the other way. So the positions would be the frequency here, okay? And that's you're moving electrons in sequence. As you move them in sequence, you create a signal that has this new position to it from the electricity moving across the crystal. And the same idea happens on receiving. It's got to receive an impulse and then another impulse and another impulse at the right rate, the right frequency of electrons moving their position so they can all send, by being in new positions, by moving at the right time, moving away or moving towards. They're creating the, quanta, then nothing, then quanta, then nothing, then quanta, on and on and on. So you kind of have to have some vision of how the thing works, but the atoms are essentially, creating the antenna for the creation of the light's frequency and polarization. So it's the same mechanism. It's just that it's on an atomic scale, very small scale, a number of atoms scale, rather than centimeters and all this stuff. And but it's the same principle that's creating the effect. You're doing the same thing to the antenna when you shoot the electricity up it, in the sense that you expand and contract the electrons. By expanding and contracting them, you reflect the world differently. So you're moving the electrons. You're not really sending energy. You're sending, the energy that's already in the universe. You're sending a gravity signal, essentially. You're taking all of this energy that's hitting everything all the time, and it's coming in randomly, and you're converting it into something not random. You're converting it into something that's on and off. So just by expanding and contracting the antenna surface, you can send your signal based on what's reflecting off the antenna, all the energy that's already in the environment. You're just changing the energy that's already in the environment. All right. That's a little bit of a preface. Okay, so I don't know exactly what you're saying there that I said. So anyway, so I chalked it up to polarization being entirely a receiver phenomenon. It's both the receiver and the emitter are atom dependent, so it would be like a domains, you could argue. So the crystals are lined up against each other, and they have all these facets and surfaces. And when you expel an electron, I would argue the electrons pile up on those surfaces, and so those surfaces become the thing that's either jiggling, and it's that surface that's creating the photon by having electrons move in and out of that fissure, let's call it. All right. All right. Where was I? Force frequency. Let's see. Entirely receiver phenomenon where force at a frequency lands on a spot of several atoms in size, affecting it. Affecting the electrons, moving electrons. So by moving electrons, you potentially create photons if you move the electrons coherently. That is, you move them in some ordered way that creates the proper frequency. Affecting it regardless of where the frequency component forces came from. So yes, to be received as a photon, the photon has to have enough energy on one piece of the crystal to be able to move the electrons on, it's like the electrons that are sending, the electrons that actually are, say, relevant are always going to be on the surface, right? So you sort of have to understand that, right? I mean, the ones that are going to be the real in the end, right? We know that, okay, all the atoms are connected to each other, so we know their electrons are all bound to each other. And what you're really doing, inside of something, if I push it this way, that means I hit this electron moves, it spreads the movement into all these other electrons. Okay, but the only electron that matters really to the force, so to speak, the force is hitting, are the ones on the surface, right? As soon as you get a certain depth into the material, there's probably not much of the gravity that's doing anything but hitting the same electron more than once, and keeps pushing on it. And pushing on it is what's pushing all the other electrons. But the surface ones are the ones that are more likely, the ones close to the surface. That movement is the one that's actually going to create your photons in the end. Their movement is the one that's reflecting the universe. Okay, the universe doesn't get all the way into the material. The universe only gets so far into the material, and then it starts redundantly hitting the same things over and over again. But they're all in pressure. They're all connected to each other. So when you hit one, you hit them all, and vice versa. When they all move, the one on the surface is going to reflect that movement. You could argue. I mean, surface is a tricky word. You can go the energy can go all kinds of depths, different depths before it hits something. But the argument would be, if you had a very thick thing, like gravity in the earth, gravity is probably not getting to the center of the earth in the form of gravity. It's getting to the center of the earth in a form that's very similar to the pressure between two electrons. It's affecting the force between the electrons. By moving the two electrons too close to each other, they move back. And it's that movement that conveys the force. All right. Lands on a spot of several atoms in size, affecting it regardless of where the frequency component forces came from. Yeah, I don't know exactly what that means. But recently you said again, photons fly through space, and you showed a piece of paper to show in 2D and 3D dimension of a photon. Yes, this is supposed to be a three-dimensional representation. So the paper isn't the photon. It's just the little dots. This is just showing the container. All right, and the container is relevant because crystals are going to interpret this thing. So the size is relevant because the row of atoms that are going to be able to interpret this thing and create a change that you can see, a surface effect, that's relevant. So for this to remain having any continuity, it needs to affect a group of atoms, not just one atom. Okay, it has to be spread over a surface. You're taking this and basically causing it to make a reaction on the surface, all of it. So all that you collect ends up with a surface reaction, sort of. All right, but recently you said photons fly through space at this dimension, right, as if they stopped spreading at some point. So these bits are all parallel, so they don't spread. What's spreading is the shape where the crystal is, right? So the crystal can be in any one of these positions when it emits a photon. So the photons, the different rays are going in all kinds of divergent directions. But these bits are always parallel to each other as they came off one surface. So they're always parallel. So they're not these individual little spots are not diverging. They're all in a straight line path with each other, perfectly parallel, as they came off a crystal surface. A flat surface, you could argue. Anyway, so I feel like I'm left with these options. A, I misunderstand semantics or otherwise. Well, yeah, I don't know what the exact point you're arguing is. I mean, I can only go so deep, right? I mean, I could spend a lot of time trying to analyze exactly how the atomic structure interprets it. I'm just saying I've given you a mechanism, this idea that surface moves, that means the world it reflects is going to be different. So if I move the surface away from the world, away from that way, right, it becomes invisible. Nothing reflects. And if I move it towards, twice as much stuff is reflecting. Get it? All right. The distance between the source atoms is small enough that the radiated force parts that just happen to fly parallel through and close enough to one another that the combined effort generally amounts to a frequency. I don't know what to say to that exactly. The frequency is about position more than anything else, I would argue, I suppose, right? I mean, these two events happen at the same time, then there'll be a frequency, right? Two things that are in different positions. They do something at the same time, right? That'll be a frequency because this one is behind this one. So whatever it pushes will have a frequency because they're both staggered. So that could be an argument, but it's more about time, right? So if we say electricity is a big fundamental component of this, the idea is that the signal moves in time and sequence. So it sends a bit, and then it moves, and it sends a bit, and then it moves, and it sends a bit, and that's the separation. So the separation would be like the thickness of the atom. That's why certain atoms create more of an effect than a different frequency of light is produced by different. All right, should be back. Anyway, all right. So the idea would be is the wider the spacing between the electrons that are doing this moving thing, would obviously change the frequency of some electricity going through. So the electricity would take longer to get through thicker atoms or atoms that had where the electricity has to move in different lines or dimensions. Then you could change what the frequency being produced would be. All right. The distance. Okay. All right. Yeah, we deal with this. The parallelness of the photon force is not generated by randomized radial spread. So the polarization, the fact that they're all parallel has to do, again, because it's crystals. So the reflecting surface is likely has to be made out of a crystal to coherently reflect back what you throw in. You're not going to get back what you threw in if it's not a crystal. All right, but by some specific arrangement of the source atoms. Right. The source and the receiver have to be antenna material. Yeah, that's probably good. I mean, you can't make an antenna out of anything, right? You can't make a radio antenna out of I don't know. You can't do it. It has to be like a metal. It's neither source nor receiver, but the photon is a ray. Somehow know how to hold a shape. So again, they're sent parallel from, and they're received in a sense on a stable surface. I don't know how to say this any better than that, but they have to be sent and received from surfaces that have a consistency, a stability. Well, anyway, which would imply some kind of interaction I don't know about, and or which I would object to. So I don't know what that even means, but whatever. I mean, there are some complications. I'm just saying the principle is that when electrons move, okay, they change how they're reflecting the universe, and if they move a few of them move in a consistent way, they'll send a pattern, okay, that's consistent, and if that consistent pattern happens to hit a crystal, it'll create a pattern on the surface of the crystal that duplicates that pattern, and therefore just recreate a reflection to the universe that is the same as what it was affected by. All right. I think it's as complete an answer as possible, or at the moment. All right, so this comment was just kind of silly. So again, more of this laughing my fucking ass off. Yeah, whatever. You don't understand the principle of equivalence at all. I understand what equivalence means, and your argument is essentially, this silly argument that, let's say, light did propel objects. You're saying being propelled by a 50-watt incandescent bulb is the same as being propelled by a 50-watt laser. You're saying they are equivalent in how they will affect me. Now, the truth is, it's going to be obvious it's not going to be any equivalence at all. Okay, the laser beam's going to burn a hole right through me, and the light bulb is going to, disperse the energy over a larger surface, and it's not going to break down my atoms and destroy them and do all that kind of stuff. It's going to, in a nice, coherent way, the energy will be transmitted from atom to atom without breaking down all the atoms and creating ions and free electrons and all that kind of crap. It's not going to ionize me, okay, like the laser beam is going to. So the two kinds of acceleration will have a net impact on me. It'll be fundamentally different. The laser beam will shoot some of my particles away very fast, okay, and leave me full of radiation, energy that I'll be radiating. And the bulb will push me in a nice gentle way that'll allow me to acquire acceleration and velocity. So the two can't possibly be equivalent, and that's the argument being made about relativity. Relativity is a stupid comparison. So in the one case of the rocket, the force is clearly being put into the rocket, okay, the bucket, and it has to be transferred through my body, through my feet and surface area. It will be transferred into me. Now, ideally, you put me in a very nice seat, and I have lots of surface area, and you can push me fairly gently. But if I am standing up and you accelerate me, too many G's, you'll just crush my little legs and crush my little parts, and it'll all just break down, and the whole thing. I won't accelerate very well. I certainly won't accelerate the same rate at the ship, because I will become a little flat puddle of goo here at the bottom. Now, the gravity, on the other hand, on the Earth, again, the argument is you don't feel it at all, okay? You're feeling the Earth stopping you. You're not feeling gravity accelerating you. You don't feel that at all. So gravity is such a benign force, in the sense it's so well dispersed, that it gently pushes you, doesn't ionize you, doesn't break you down, doesn't wobble your legs, doesn't do any of that. It's the Earth pushing back. Okay, so there's two forces here. The idea is they're saying these two are equivalent. They're saying gravity is equivalent to getting pushed by a rocket. No. The ones that's equivalent is this, the counter force. This is the counter. and counter force. This is the counter force. So this is something you banged into. If you were free falling, you'd be like, ah, la, 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 la. Nothing's, there's no equivalence at all. No equivalence between free falling and this, okay, clearly. Being pushed by a rocket, very different from being pushed by gravity. Not the same thing at all. You won't feel it the same. It won't affect your body the same. Nothing equivalent. Yes, being pushed by the Earth, being stopped, same thing as it being pushed, right? You're being pushed in the opposite direction. These two things are equivalent. The counter force. So solid objects hitting you, you could argue, that's equivalent. Yes. Okay, so if I take a thing and I bang it into me this way, it's going to be the same as if I banged it into me this way or this way. Yes, of course, hitting me with something is equivalent. All right, but the forces are the way the force is implemented or imposed on me in this example and this example are as different as a laser beam and an incandescent light. Couldn't be more of a difference. So that's why the equivalency principle is BS. It's bullshit. There is nothing the same about this force pushing me, the Earth pushing on my feet, and the force of gravity, which is pushing me, every little atom almost is being affected by the gravity. Not equivalent at all. Alright, I don't even know why I bother writing this. You're not writing anything that matters. But first of all, the whole point is that you can't tell. So this is more horse shit. I mean, Sean Carroll in the video admits that you possibly could tell by just measuring the difference in the gravitational potential between 2 points. So if we had instruments capable of measuring how much gravity is on my head, how many meters per second versus how much is on my feet, how many meters per second, that I in fact could tell. So again, it's just more horse shit. And I'm arguing that even Einstein admits that, yes, all you need is a light clock and you can tell. The light clock will be your speedometer. The faster you go, the more the light's going to look like it's falling down when it's not. Okay, it's going in a straight line through straight space, and that you've moved in space, and that's the thing that's changed. So it'll be a perfect speedometer. It'll tell you exactly how fast you're going. I mean, if we could really see small changes in photons, like if we had some connection to that 3 million meters per second thing, we could do it right now. I could set up a light clock and I could measure the little change in the light depending on how I'm moving in the universe. It would work. Okay. There's nothing between, so okay, anyway. Why I bother writing this? But first of all, the whole point is that you can't tell when there's nothing in between. So speculating that you could, if there was, doesn't even have anything to do with it. Nothing in between what, idiot? Moron? Kook? What the fuck are you talking about? Secondly, well, the first argument failed. The argument you make about standing in the rocket ship is exactly why it is the same. So bullets are the same as cardboard boxes or something. If I move a cardboard box at a certain speed and hit you with it, it's not going to do much because it's going to spread the impact all over you, and it's going to fold and bend and do lots of things. Where I hit you with the bullet, it's going to bore a little hole in you, and that's all. The Earth is accelerating you at all times. Yes, from head to toe. Duh. Exactly what I said in the video. Duh. Alright, and you counteract that acceleration by exerting forces on the ground. No, the ground fights back. I mean, whether you exert the force or whether it fights back, I mean, obviously it pushes back. So, yes, you have to attempt to go into the Earth before the Earth can say you can't do that. But the point is, it's still an equal but opposite force. It's a real force. It's real pressure that's pushing you up. So you have to incur, you have to push into the earth, and the earth has to push you back out. So it's in fact, you can logically understand that's actual movement. It's just that it's back and forth movement, where in the rocket ship example, there's no counter force, so all the movement is free to keep going in one direction. Yes, if you go in one direction, you cover distance. If you go both ways, you don't cover any new distance. You don't move to a new place in space. Your acceleration is wasted in the sense that it doesn't get you any distance, but you're still accelerating constantly. Okay. When you are in the hypothetical rocket ship, you have a certain momentum, and so it doesn't matter what your momentum is. We're talking about acceleration. So again, get with the program, so to speak. And so your head wants to stay where it is. No, the fact is the force can't get to your head without going through your feet. That's the argument. There's no magical force in the rocket ship. There's no raindrops hitting you. There's just a floor hitting you. Okay. You have a certain momentum. Okay, and you want it to be where it is, or your whole body, for that matter. So again, there's nothing about what it wants to do. It's just that it takes time to move the force through all of the atoms of your entire body. So it takes time for the pressure at your feet to get all the way through your body, and you actually feel it, because it does have to move all your atoms, and you end up feeling that force where you wouldn't feel it if it was gravity that was pushing you, because it pushes you so gently, so perfectly, in the sense that it pushes you on the subatomic scale. It's not forcing a bunch of atoms and blood and tissues to push into each other. If it is then accelerating you at your feet, you must counteract the temptation of your body to stay. So more of this crap that it has something to do with the resistance to movement. There's no resistance to movement. It's just that you have to actually hit something with a force to move it. You have to get the force to where the electrons and protons are. You have to hit the electrons and protons with a force. The only way you can do that is to push the other electrons next to things towards the other electrons, so they feel the force between the two electrons. So you have to convey the force by moving the matter. All right. So where it is, i.e., you need to change the momentum of the rest of your body in the exact same way as you would need to on the Earth. So that's just more nonsense, right? Because the only thing we're talking about is whether there's an equivalency between how gravity imposes acceleration and how a rocket ship floor imposes acceleration. And there's nothing equal about them, in the sense that there's a certain amount of energy, but the energy is conveyed into the mechanism much more efficiently through gravity than it is through pushing feet. Okay. The exact same way as you would need on Earth, though the forces within the body with which you counteract a collapse. So again, I don't know, there's nothing to say. It's just kind of silly to compare two force environment with one force environment and say they're equivalent. No, one has two forces. Not equivalent at all. So yeah, both cases are exactly identical. So that's what you just said. So it's exactly identical having two forces acting on a system than just having one force. That's exactly identical. And it's exactly identical to hit you with a laser beam as it is 50 watts of incandescent light. Exactly the same thing. No, not the same thing at all. Spreading the energy over as many electrons and protons as quickly as possible is a lot different than shooting people with bullets. Not going to bother watching more. Well, not going to bother interacting more. So, fuck you. People, they so suck. Alright, so on to Sean Carroll, I guess. And drivel. Nonsense. Rubbish. So anyway, their understanding of the universe. So they keep saying they know what a particle is. They have this is particle physics, but and when it comes down to it, they don't believe particles exist. They believe the universe is made out of some sort of jellyfish swimming in an ocean of some kind.
An ending point in sight. We're closer to the end than we are to the beginning. Sorry about that. So we're going to be finishing up with a slightly different kind of ideas. We've done a lot of work.
So he finishes up with these. So 17. So 17 of his biggest ideas is actually getting to matter, right? What the hell that is. That's 17th on the list, which is kind of hilarious, right?
Recently on building up quantum field theory and the standard model and gauge theories and things like that, and we have other fish to fry, as it were, so we're going to be less about that. This video will still be about quantum field theory, but it'll be about a more tangible aspect of quantum field theory. So the focus and the biggest ideas will always be conceptual. It will always be the big underlying ideas, not the...
Oh, this is just so funny, right? Because there's no concept. There's not a single drawing of anything except mathematical equations. There's no concepts here.
Gritty of this and that, but now we're going to get into things that are a little bit more relevant, a little bit more not relevant, familiar, let us put it that way, easily grasped to us. So even in this video on matter, so what I should say is, having said that, even though this video is about matter, you might think, well, okay, it's going to be about materials and things like that. And you know,
yeah, no, it'd be nice if it was about the difference between things that are moving the speed of light, forces, and the stuff that isn't moving the speed of light that has to be pushed somewhere, the matter. And, you know, it'd be nice if you made that simple distinction. I mean, I don't see how they see it any other way. I mean, I always, okay, I mean, it's like from 5th grade on or something, had this concept that, yeah, there's the little stuff, okay, moving really fast, and that stuff is pushing the matter stuff. I mean, what other way do you look at it? I don't know how you people look at it any other way. I don't know how you think about it any other way. How does it make sense to you in any other way? Electrons and protons are fundamentally different than photons. You know, fundamentally different things.
No, it's really not, because I don't know anything about that stuff. You should go to other people who know more about that for those topics. I want to connect some of the conversation we've been having about quantum field theory and the underlying laws of physics to the features of matter that make up you and me. Okay, in particular, most of today's idea is going to be about a single feature of matter, which is that it can be solid, right? That a table is solid. You can't just put your hand...
Yeah, and it's solid for what reason? Because electrons hate each other. That's really it, right? I mean, the protons have been rendered sort of inert, okay? Their effect in a lot of ways, just because they are trapped in the tiny little nucleuses. And they're really, you know, because they have an electron between two protons, right? I mean, the electron is dispensing with all the energy that would reflect between the protons. So the protons are able to get very close together, okay, in their little package. And that whole package has to get moved, essentially. You know, you push on one thing, it pushes on the other. But the real key to understanding anything is to understand that electrons, I can't move an electron without moving the other electrons. I mean, they have energy bouncing between them. So they're constantly aware of where everybody else is, essentially, through those reflections. And if I change one over here, it's going to affect relationships with all these others. And you know, so any pressure I apply in a direction is going to be transferred to everybody eventually, and they'll all be dragged in a direction. And even if I move the nucleus, likewise, that's going to move the attractive forces, and they're all going to have to rebalance again. So everything moves because there's energy between all these bits, tying them all together, and pressure from the outside, and all this kind of stuff. And it's a system, and the system takes time for all of that. For any one movement, it takes time for that to be transferred, so it takes time to accelerate everything, but it does happen eventually. Eventually what goes in will move the stuff, and it will, you know, push into some new world through that event. But yeah, that's you know, that's the distinction. We have electrons and protons. That's the known reality. The neutron is really just both of those things together. So that's it. That's you know, that's all that's the matter, and the rest of it is all just this stuff we call energy, in the sense that it's this stuff that's moving the speed of light, and there's a bunch of that in here. Okay, there's a bunch of that in patterns inside of here. Okay. And so you're just transferring the energy. You transfer a little more into here, and it comes out somewhere. This has equilibrium. The atom has a kind of equilibrium. So whatever comes in eventually comes out.
Hands on it and fall right through. This might not seem like a question, but we'll ask it anyway.
So why? The why would be is that if you push on something, things are solid, because to move them, just as I just pointed out, I have to move all this whole board. I can't move just these electrons. I have to move all the electrons because they're all going to push into each other. So all of them are going to have to be accelerated or moved for me to move into the board, because the electrons are feeling the pressure of all the other electrons, all of them. So yeah, the physical fact will be as I'll push some of the electrons into the surface, that'll create the same opposite reaction that pushes me up on Earth, because the chemicals, the atoms, are incapable of compressing. They already have energy in them. They're not going to compress. They can't get any smaller without pushing back. So that pressure will push back. So there's just no way I can shove matter into matter without shoving electrons into electrons, and electrons will not be shoved into each other.
Why is matter solid? You might remember way back, in one of the early videos, we were talking about...
Because it has force in it. Because the electrons, again, are like ping pong paddles, and they have ping pong balls bouncing between them. And you can't push them closer together without forcing there to be more interactions that push them back apart. They'll fight back. You push them closer together, more pressure going out. They'll fight back.
But the fact that just before quantum mechanics came on the scene, you could have imagined, in the late 1800s, you could have imagined a version of physics where there were two different kinds of stuff. There were particles that made up matter, the particles that we would now know as the electron, the proton, the neutron, and so forth.
Right. It seems to work, and it still seems to work, right? They don't draw you any model of an atom that has muons in it, or puons, or kuons, or zuons. There's no drawing of an atom working with all this other crap, and antiparticles, and anti-electrons, and anti-protons, and anti-neutrons, and anti-this, and anti-that. They don't draw you any model of that, because it's nonsense. Because that's not how it really works. We know these are the only working elements. Everything we know, we know it from electromagnetism and all that stuff. There's no room for any of these other stuff to be doing anything. It's all about what a proton and an electron are doing. And we know that if I change their position, I create magnetism. And they don't get the magnetism part, right? They think magnetism has something to do with electrons spinning, and having some sort of magnetic moment, because they're somehow a dipolar magnet. But no, the atom is the magnet. Charge and magnetism are the same force. It's the same force. It's just being expressed in a different way. Magnets do it from the inside out. Charge does it on the damn surface. That's the difference.
There were forces that pushed and pulled the matter together. That's not exactly right, but there's a very close relative to that. And so today we're going to explore the matter side. When we talked about gauge theories the other day, we were really talking about the forces side of things. So why is matter solid at all? Now, you might think, well, once you know about atoms and particles, this shouldn't be a difficult question. If you have some collection of atoms, you can just stack them on top of each other. Or maybe you could, these are supposed to be atoms, not just bowling balls.
So he's making it, ridiculous in the sense that, no, we already know their atoms aren't like that. But we do know electrons are like that. So this would be a better argument if he said, well, what are the electrons on the outside of the atom doing? Because we know the electrons are on the outside, right? So it's really just about what electrons are doing.
Why can't you just stack things on? Or, of course, atoms can stick to each other, right, with chemical bonds, and you would imagine there is some...
Yeah, and they're sticking to each other, taking advantage of a very specific circumstance where an electron can sneak in, and we could have two atoms there can be a missing electron. That is the place where the positive force is visible, and that obviously an electron would tend to want to fall into that positive space and get into a relationship with these other electrons, and that we could share. They could share an electron, physically share it. Okay, where the electron stays exactly where it was. So if they understood a magnetic magnetic model for the atom is just so much more rational than the stupid gravity, momentum, orbiting nonsense. So that's where it really goes wrong for them. I mean, if they understood a magnetic, if they understood that the electrons and protons are not swirling around doing anything, they're trying to stay as stable as possible. They're just like magnets would do. So if I could create monopoles of magnetism, I could arrange them where the repulsive pressure between the electrons and the attractive pressure between the electron and the proton would be in balance. And if I tried to move the electron in, it would get closer to other electrons, which would push it back out. So it reaches a stability. And there's 100 kinds of geometric configurations you can make that are stable like that. Just 100. A little less.
That makes sense. But then you remember, we're drawing atoms as little spheres. We know better, right? Atoms are not little spheres. Atoms are quantum objects.
So this is where it goes all loopy, right? Because now we're going to call them quantum objects. So again, even by their own physics, it's kind of a silly way to describe it. You know what an atom is, okay? It's plus on the inside and it's minus on the outside. So why are they trying to describe it some other way? We know this is what it is. All right, the electrons are out here, okay, and the positive charge is in here. And so, yes, obviously atoms are naturally, don't like each other much. All right, but obviously also if I have an ion, that is I have a hole, okay, it's very likely that these two would attach to each other and they would share this electron, and the two atoms then would stick to each other. So in that circumstance, and you could also understand if I banged into two atoms, I bang an atom into another atom hard enough, okay, that I could displace an electron, and they would end up sharing one, of theirs. So if I got past the repulsiveness, so the two atoms don't like each other, but if I hit one in hard enough, and I knock its electron out, then I have the one electron, and now they're really happy to stick to each other very well. So that's why heat creates compounds, is because you're basically saying if I smash a little piece of atom X into atom Y, right, I do it hard enough, I can create a good bond. Might even knock two electrons out and then they'll share two electron holes. I can make a very stable compound. Not that complicated. They know this stuff, so I'm just saying this doesn't even make sense to say it's a quantum object. What the hell is that? What is that mush?
Particularly the size of the atom, we talked about in the video on scale, is set by the Compton wavelength of the electron. It's really set by the Bohr radius, which is the Compton wavelength divided by the fine structure constant. So the electron has a wave function, right? The electron wave function is wavy. It's sort of smooth, and you could.
So it's sort of like a jellyfish, and electrons are jellyfish, and protons are jellyfish, and they make opposite waves somehow, and they send messages to each other, little messenger tons. Their little stingers get entangled. I don't know, it's freaking baby talk.
Easily imagine deforming it. So the question is, why aren't they squishy? Why aren't atoms squishy? This is one question.
Because they have energy in them that can't be compressed without creating more energy. So if you bring them closer together, you effectively create more energy, but you create more interactions. Interactions are energy. So proximity is energy. The closer two things are, the more potential for energy there is between them if there's energy trapped between them. And that's just a fact. And that's the fact that makes atoms difficult to compress. You can certainly do compress them, because by compressing them, by changing their shape, you change their polarity to the rest of the world. You change how much of this positive gets out by compressing. By making the electron closer, you change how much of the proton force you actually see over here, and vice versa.
By which I mean, it looks like squashy. Let me make it look more like squishy. By which I mean, you could easily imagine, it didn't look like squashy, it looked like squishy. If I have two atoms like this, one right on top of each other, and I push them on the bottom and on the top, why don't they just squeeze down to more elliptical shapes so that they're much smaller? Okay.
I would argue that they'll stay the same size, right? The actual area will be the same, but their polarization will change rather dramatically. So here you're pushing electrons further away from each other, but you have more of them on this outside surface, and obviously you're closer to protons here and here than you were before, so this would become positive. So these two sides have become negative, these two sides have become decidedly positive, and I'd say that's exactly how magnetism and electricity work. Changing the shape of the atom changes its polarity.
Well, they're much smaller in one direction, maybe wider in some other direction. Why don't they just deform? They're just waves, after all. And
they're just waves. Why don't the waves? So this is just a wave. This drawing, the circle's a wave, whatever that means. What is that? They're just waves, after all. What? I'm just saying. Why do you people think this is a rational description of reality? And then God said the wave is good. I'll make wavicles. What the hell is it? It can't make any sense out of this crud.
The answer is sort of implicit in what we talked about when we were talking about wave functions and the shape of atoms in the first place. Namely that the electron in a hydrogen atom, or even more complicated atom, its wave function has the shape it does because it's trying to minimize its energy, right? It's trying to minimize its energy.
So, more nonsense. It's trying to stay stable. So when they say minimize energy, they're really just saying, is it in a place where it's not moving too much? The more it's moving, the more irritable it is. Obviously, it's in a state that's not ideal. So, yes, everything is not seeking quiet. It just happens to go where quiet is. If there's low pressure somewhere, it seeks it out. So wherever there's a pressure differential, it'll always seek out the lower pressure. And that's it. So you just want, when you put it in an environment where there's very little pressure difference, it's very happy and peaceful and restful. And the more agitation, the more, you're going to have that. Yeah, it's just a heat argument, really.
Subject to certain constraints. Maybe there are other electrons in the way, it's being attracted by the nucleus, and so forth. So if you can imagine taking an atom and squishing it. There's no problem with imagining doing that, but its energy would change. And since its energy is...
So the energy of the atom doesn't have any energy. There's the electrons and protons. They're the ones reflecting, trapping energy. So the atom itself, you wouldn't talk about it being a mechanism. The only thing that really matters is the electrons. The electrons are the relevant piece here. Again, the nucleus is it's just so distant from the daily activities. The nucleus moves on a weekly scale, where the electrons are working on a second scale. They're the real active players because they're on the outside, which is hugely important.
Already at the minimum, given the constraints it's subject to, the energy has to go up. You have to put energy into it. You might imagine that's not much energy, right? Like, how much energy can it take? It might be a squishy...
So any energy that hits it from the outside that's an extra piece of energy has to be felt as pressure. It has to... This just as we hit the Earth, we're causing movement in the Earth. It's heat. It's a real event that's going to take place. And it's going to push back. That pressure is going to push back.
Kind of springy thing. But in fact, it's...
You're pushing the ping pong paddles closer together. The ball's bouncing. You can understand there's more impacts the closer they are. Each impact has the same amount of energy. So obviously that's the pushback.
A lot of energy. If you changed, in a table, if you changed all the electrons' energies by 1%, that turns out to be an enormous amount of energy. I didn't actually calculate it. That's a good homework problem. I predict it would be something like an atomic bomb's worth of energy if you wanted to squish all the atoms in a table to change their electrons' energy by 1%. So there's a reason...
So he bothered to calculate it. Obviously by 1% closer, would be the argument. I mean, to add energy, you'd have to be making things closer. Again, you lose energy when you make things further apart. You gain energy when you make things closer.
Why electrons want to remain spherical in atoms? It's because they're in their lowest energy states already. It would take a lot of energy to change them.
So lowest state just means the state at which it's stable, or the state at which the geometry is stable. You could argue. The distance that makes the magnets just stay where they are. So if I levitate two magnets, there's a certain amount of magnetism, and the magnet will levitate at a certain level. And all you're doing is changing, by adding other influences, you're just wobbling that level. But wobbling it is not increasing its energy, it's increasing the energy trapped between it by pushing down on it. And then it pushes back. And then you push down on it, it pushes back. The vibration has to be caused by changing the pressure.
There's another question. Why don't they fall on top of each other? Why don't atoms go on top of each other? Why?
So the easy answer to the question is because charge. That's why. Electrons are charged. They're repulsive. They have a ping pong ball bouncing between them, and you can't get closer without applying pressure to force them to be closer. You have to continuously push on them to force them to be closer.
They solid individually. So we say the tables are solid because they're made of little atoms, right? So that presumes that the atoms themselves have some ability to take up space, right? To occupy volume. So why can't we just imagine going from two atoms, pushing them together, and then this goes into one atom right on top of another one?
So again, he just totally ignores that we already know they're negatively charged on the outside. Both of them are essentially negatively charged objects. You can't get around it. The closer you get to them, the more you see the negative charge. So this again is the argument that yes, from a distance, the two forces blend into almost nothing. But as soon as you get close, okay, then you can see the difference between the red and the blue light, right? So I could have a red and a blue light shining, okay, and from a distance it'll look like purple, okay, that's all I'll see. But the closer I get, right, I get right up next to the blue light, I'm going to see more blue and a lot less red. All right, so obviously that's why two atoms can't crash into each other, is because the electrons will feel each other's reality, right? So you have two atoms, you have one over here, okay, and you have one over here. Long before they get really close to each other, this electron and this electron, the little ping pong ball is starting to bounce a lot more. Okay, and it's the inverse square kind of, well, it's the R rule. So, the more half the distance, twice the force. So as they're getting closer, this pressure is increasing, right? I mean, pressure increasing. So as this gets closer and closer, there's already more pressure. It's fighting back. They're communicating from a foot away. They can feel each other's pressure to some extent. And obviously, the closer they get, the more these things start increasing by the millions of more interactions. So you're increasing the number of interactions by huge numbers, tens of thousands, let's say, more. The ping pong balls bouncing, hitting the paddles 10,000 times rather than 100 times a second. So obviously, this is a tremendous amount of force that's building up, saying you can't go here. This electron can't go here. So it's really a battle between electrons. It's not a battle between atoms. It's just a battle between electrons. And the electrons are just saying, you can't do this. So this electron feels this more pressure coming from this electron. It conveys it to this electron. It conveys it to that one. And it says to this whole atom, you can't go there. It makes more pressure. You go there, it makes high pressure here, okay? And now this becomes low pressure relative to this. So obviously you're going to go this way. But I mean, not to even concede that we already know how atoms are structured, and we know it's all in a game of electrons. All of chemistry is what electrons are doing.
Right? What's the danger of that? It's not quantum mechanics per se that is the problem there. There's no problem with having two electrons overlapping in their wave functions. I mean,
so in his wacky book, that's possible. Two things can occupy the same piece of space because, I don't know, even jellyfish, even if you believe their silly wavical bullshit, why would you think two of them can be in the same place at the same time? Come on. They hate each other intensely. How do you do that? Oh, that's right, you can't do that.
Electrons in an atom do that. But they don't do it arbitrarily. There are rules that they follow, and that's basically what we're going to be talking about today in today's video. To give away the secret, which I'd like to do, we're going to be talking about the properties of fermions. Fermions are a certain kind of particle named after Enrico Fermi, famous Italian-American.
So there's absolutely no point in doing all this, right? Fermion versus boson or whatever. There's no point in doing this crap. We know the difference. The difference is forces moving the speed of light and matter bits, electrons and protons. And that's all there are, electrons and protons. Neutron is composite. So that's all there are. Electrons and neutrons, plus minus force, charge, magnetism. It's all You don't need bosons. You don't need tau thingies. None of that shit does anything. So why are you including it? None of it, even in their accelerators, it doesn't exist for any amount of time. So it's not obviously a player in any way. So, and all it really is energy, right? All of these new particles are just ways that you can move electrons and protons. And the faster you move the electron, they call it something new. But you hit it with a longer ray of energy, then it's a new particle. It's the same particle. You're just pushing it with more energy, more pressure.
Physicist, and they are in contradistinction to bosons. And roughly speaking, bosons named after Professor Bose, whose first name I can't pronounce, who's an Indian professor. So Bose hooked up with Einstein to invent Bose-Einstein statistics, which are particles of a certain kind, roughly speaking, particles that like to pile on top of each other.
Right. So there's no such thing. So it's just there's no evidence that anything ever piles on top of each other. So again, they don't have any evidence that anything ever piled on top of each other.
Particles that actually prefer to be in the same place, if you have identical particles of the same species, are bosons. Fermions obey what are...
So this is more, of the abstract physics where you make your infinite gravity well by compressing matter to insane dimensions. And the only way they could do that, the only way they can create their black hole gravity with actual matter, is to sit there and pretend that they put particles so close to each other they create an infinite amount of ping pong. It's like me moving the paddles, infinitely close to each other at the speed of light. You know what I'm saying? I can sit there and make this argument that I can somehow compress them infinitely. No, I can't. There'll be a certain distance, and I'm now close as the photon is, and the photon can't move anymore because I've sandwiched it so close. It can't cover any distance anymore. Can't create any more energy. They think there's an infinite amount.
Called Fermi-Dirac statistics, after Fermi and Dirac, and they like to take up space. Fermions do not like to be on top of each other. So the glib answer to why atoms don't want to be on top of each other is because electrons, which are giving you the size of the atoms, are fermions. They take up space. They don't want to be on top of each other. But we want to get closer to why that's actually true. Okay.
And so are protons, right? So what's the point of this argument? So where did you get to the stuff that wanted to get on top of each other? Oh, that's right. You never got to that part.
So the name of this principle that says why not is that says that this doesn't happen, rather, is the Pauli exclusion principle. So again, this is the motto, electrons take up space, is a very cute little retelling of the Pauli exclusion principle, which is a precise quantitative statement, which says that two electrons cannot be in exactly the same quantum state at the same time. Now,
not in the same quantum state. So, and the quantum state is where you are in space, which is kind of a silly thing, right? You're thinking about its properties. You don't think about its properties being, well, I'm in this space. So to make where I am in space a quantum property like spin or like polarization or some other quantum property is kind of silly, right? It's not really a property of the thing. It's a property of the environment. So it's, Well, anyway, probably enough of this crap. You can just see it. It has nothing to do with real physics. There's nothing about charge, which is the thing moving all the atoms and all the bits, and it's totally disconnected from the reality. It's just a terrible pile of mush. But anyway, so maybe I'll listen to some more of this and see if there's any real funny bits. But it looks like it's he's just going to plow into his mathematics, and that'll be the end of any kind of conversation about reality. Yeah, there it is. So he's got his little psi symbol, our wave function times blah, 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 wave function, blah, 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 blah. Useless tripe. So, anyway, till the next time and such. I don't know why you find this irrational description of reality at all appealing.